All right, let's begin with a word of prayer. Dear Heavenly Father, we thank you for this weekend just completed. Pray with the students today. Help us to just understand just a little bit more about complex analysis. Again, Lord, we thank you for your many blessings for us. We thank you that you just came to earth and died for us if we're just willing to accept you, your sacrifice for us, and repent from our sins and turn to you, Lord. We thank you that we can have your forgiveness and be righteous by your righteousness, Lord. And thank you for this day. I just pray be with the students and just pray that you'd be glorified in this class today, Lord. In your name I pray. Amen. All right, so I want to talk about harmonic functions. There is an unfortunate typo in the notes that I will get to eventually. So here's the definition. If I have u, let's say it's a function from some subset, I don't know, the subset of the complexes to the reals, and well, complexes, I mean, I usually say R2. Fine, let's say Rn. Let me be greedier. So suppose you've got a real valued function on some open subset of Rn, and it satisfies the following equation. The divergence of the gradient of u is equal to 0. Then u is harmonic on V. Now, the divergence of the gradient is also known as the Laplacian. This is basically u, partial squared, partial x1 squared, plus partial squared u, partial x2 squared, plus plus partial squared u, partial xn squared equals to 0. So that's, generically speaking, the Laplacian in n dimensions in a function which satisfies that on some subset of Rn is said to be harmonic on V. There's a vast literature studying these things, but in the context of the plane, in the context of n equals 2, the full force of complex analysis comes to bear, and they're really, really nice, simple theorems about these things. But harmonic functions is something you could make a career out of. You could study them on curved spaces, whatever. So for us, n equals 2. We just have what? We have uxx plus uyy is equal to 0. Where, of course, I'm using the usual, you're fine, you can, no one cares. You just go where you want to go. It doesn't matter. It's fine. See here. So that's, Laplace's equation. All right, in solution to Laplace's equation, it's called a harmonic function. So I want to talk about those for a couple minutes here. So the main result here is, sorry, trying to get to my silly numbering. Is that if f, which is equal to u plus iv, is holomorphic on a domain D, all right? And what was a domain? An open connected set, right? If f equals u plus iv is holomorphic on a domain D, then u and v are harmonic. Now, the proof of this requires me to talk a little bit about a kind of more subtle issue with complex analysis. So I need to make a remark before I give the proof. If f prime of z, which remember is ux plus ivx, which by the way is also equal to what? Vy minus iuy, amongst other things, right? Someone proud they knew it? Very good. So if the function is complex differentiable, right, then there's something really interesting that happens in the complex domain. It's automatically true that the mapping z maps to f prime of z is continuous. Now I need some more fine points here, like I'm talking about with respect to some, let's say, domain or something. So I'm saying that, if f prime of x, f prime of z is equal to ux plus ivx over some domain, then it's true that the complex derivative is continuous. Now, why is this is interesting? In the real case, right, in contrast, in the real case, you could have something like, I don't know, how about this, f of x, and here I can do two variables. It would just be a stupid two-dimensional example. F of x y is equal to x times the absolute value of x. So here, the Jacobian of f is what? Partial f, partial x, partial f, partial y. What's the derivative of x times the absolute value of x anyway? I'll do the easy part for this. 0, 0, 0. So there's just a first component here. You're like, you're in the real, you should do this instead. Fine, fine. You made me, you've driven me to it. There, are you happy? Okay, so what's the derivative of x times the absolute value of x? What is this function x times the absolute value of x anyway? It's an important example in real analysis. It's the parabola like this and the parabola like that, just pasted together at the origin. It's like a cubic, but it's not. Right? It's like two half parabolas pasted together. But if you differentiate that, you get 2x. Well, that's not quite true. You get what? You get 2 times the absolute value of x. Because the basically, here's the derivative. So you notice then that in the real case, I can have a function which is differentiable at every point, right? This is differentiable on the plane, no problem. I mean, 2 absolute value of x is a formula which makes sense and is continuous, right? Oh man, this is not the example I wanted. Ah, curses. This is still continuous. Ah, phooey. But what happens if you try to calculate second partial derivatives? Sorry, the example I'm looking for is more subtle than this. I mean, my go-to example, for example, of something which is differentiable at a point but not continuous, but the derivative's not continuous, is this thing, right? Here's an envelope. This function will have derivative 0 at 0, but the derivative is discontinuous at 0 because it's increasing and decreasing infinitely many times dense to the origin. This is something like, y equals to x squared sine 1 over x is the function for x not equal to 0. So here's a function which is differentiable at 0 but not continuously differentiable. And that will certainly not fit the bill of my remark in the complex case. This, my first example is not quite as subtle as this one, but this one has the property that it's once real differentiable but not what? If you were to, right, yeah, if you try to calculate partial squared f partial x squared, it does not exist at the origin, right? So my point is, let me just put it in a box and get rid of it. In the real case, it's not so simple. You don't know for a domain that if the derivative exists, it's continuous. It's something very special about complex analysis. And we're going to have to work a little bit to prove that. Anyway, that's a future event. So this is a remark from later in the course. But what that means then is, for my proof, I'm going to assume that result, okay? F prime of z exists for z in some domain D. Then, since z maps to f prime of z is continuous, what's that say about second partial derivatives? It also implies that like uxx, vxx, vxy, vy, all of them, all the second partial derivatives are continuous. I mean, you can go further. In fact, partial derivatives of all order have to exist, and continuously so. I think we only need up to second order, though, for the purposes of the proof I'm about to give you. All right? Okay, so that's kind of a technical point, but I do need the existence of second derivatives. I'm just telling you we will get to that later. All right? So getting back, we're assuming that f is holomorphic on a domain D, right? Which means f prime of z exists at each point, right? At each point, there's some open set in which f is complex differentiable. And then what are we trying to show? We're trying to show that, u and v are harmonic. So what do we know then? We have what? Ux is equal to vy. And what else do we have? Uy is equal to minus vx, right? Let me call that equation 1, equation 2. We have those on the whole domain D, right? So what can we do? How about differentiate one? With respect to x, what do we get? We get uxx is equal to vxy. Oh, I'm sorry, guys. Let me just use a less ambiguous notation, since the whole proof here is mostly about commuting partial derivatives. Let me use a less ambiguous notation. So I'm going to rewrite this as partial x of u is equal to partial y of v. I'm going to rewrite this as partial y of u is equal to minus partial x of v, if you don't mind. So then partial x of u is equal to partial x partial y of v. So you can see the order of the differentiation more clearly. And how about if I take equation 2 and I differentiate, equation 2 with respect to y? What does that give us? That gives us what? Partial y of u is equal to what? Minus, I'll pull the minus outside the derivative, partial y partial x of v. So let me call this equation 3 and equation 4. You guys with me? I hope. Then what? So if I add equation 3 and equation 4, what do I get? It gives me partial squared x u plus partial y squared u is equal to partial x partial y v minus partial y partial x v, right? But Clairaut's theorem, which there must exist some semester in advanced calculus where I would prove that. It wasn't this semester, but it is in Edwards. So you can prove that if you have continuous differentiability of the second partial derivatives, then you can swap their order. There do exist pathological real examples where if you don't have continuous differentiability, you can't swap their order, even though they both exist. But they do exist, and so the partial derivatives commute, and these cancel and give us 0. Therefore what? In the other notation, uxx plus uyy is equal to 0 on D, hence u is harmonic. Yes, sure?
So there's that theory you're talking about that means that partial x partial y is equal to partial y partial x, and that's why that equals 0?
Right. I need the existence of the second partial derivatives. I need that they exist and that they're continuous.
Okay.
So then I can swap the order.
Okay.
It's Clairaut's theorem, yeah. I think it's Clairaut's theorem. Sometimes I think it's called Fubini's theorem. I don't know. I think Fubini proved something really, really complicated and deep that we call a bunch of things Fubini's theorem, although they're kind of like low-level implications of something much deeper he proved. And besides, people just like to say Fubini because it sounds awesome. I mean, should have named a kid Fubini. It'd been awesome. Hey, Fubini, come over here. Rolls off the tongue.
Maybe like a pet.
Maybe a pet?
And what's the difference? A little annoying small dog.
The difference is children are something I would have. A pet is not.
Why would I'd be vice versa?
You'd be vice versa?
Yes.
That does sound like your superhero name.
Being or vice versa.
I can see it. I can see it. What is the power of vice versa? She confuses people with laughter.
I'm confused.
See? It's happening even now. Oh, I claimed that u and v were harmonic. What's the proof? The proof of v being harmonic is nearly the same, but there's a more fun way to do that. So you could prove that v is harmonic by essentially the same argument, right? Just isolating vxx and vyy from the Cauchy-Riemann equations. Or an alternative argument you could say is this: if f equals to u plus iv is holomorphic, right? And so in the notes, I have holomorphic replaced with the word. I say that f is harmonic in the notes, and that's unfortunate. I'm not sure what's happening,
I don't think anyone is.
but I'm amused.
I'm not sure what's happening either.
Actually, I'm more intrigued at the moment.
I probably should have just walked out like a normal human being. But I don't have disrupted the tape recording. My nose is running. I'll be back.
What kind of friend are you? Okay, if f equals u plus iv is holomorphic, then another thing you might notice, and notice that the real part of f is equal to what? It's equal to u, right? Well, if you were to multiply this thing by minus I times f, which is equal to what? Is equal to minus iu plus v, is also holomorphic. Which is a simple consequence of the linearity of the complex derivative, right? You can pull minus I out. So if f prime of z exists, then the derivative of minus I times f also exists. It's minus I times f prime of z. So it's also complex differentiable in the domain at each point. It's holomorphic. But what's the real part of this function? Right. So by the previous argument, this has the roles of u and v switched. So the argument I just made for u, I can now do for v with the new function, hence it's harmonic. Or you could just tweak our original argument ever so slightly to get get the proof, right? Any questions? Now, there's a natural question here to ask: is the converse to this proof? Is the converse to this theorem true? I mean, here I have this direction, right? Is this true? Right? If u and v are harmonic, then f equals to u plus iv. Is it holomorphic? The answer is, what do you think? The answer is no, generally speaking, yes. But with a relatively mild topological condition on D, it's true. For example, Gamelin proves that if D is like a rectangle, if you have harmonic on a rectangle, that implies f is holomorphic on the rectangle. And indeed, as we'll go on, we will replace this with more and more complicated shapes. I will not try to answer the question of the most general possible shape on which this is true. You should read something like Ramir if you're interested in that kind of question. But yes, a converse does happen to be true. All right. So then a very popular exercise is as follows. Given a function u of x comma y equals to formula, all right, is u harmonic? And if so, find its harmonic conjugate. What's a harmonic conjugate? I haven't introduced that term yet. And that's a misuse of the apostrophe. I'm sorry, I feel bad for that. It's, yes. What does it mean for v to be the harmonic conjugate of u? Definition, u harmonic and f equals to u plus iv, holomorphic, implies v is harmonic conjugate. In other words, it's the other half. It's the other piece of what you need to get the complex differentiable function. So like a given harmonic function is half of a holomorphic function, let's say. This is all with respect to a particular domain. Okay, so let me make up an example that won't take us too long. Let's see here. How about u of x comma y equal to, goodness gracious, I don't know. E to the 2x cosine of 2y. Is this harmonic? So what do you gotta do? Uxx is what? 4. Yeah, 4u actually. Because it's 4 e to the x, e to the 2x cosine 2y, which is 4u. Fine. Do you feel better? Is it better? But my point is, that's 4u. Okay. What's uyy? Because when you differentiate cosine twice, you go minus sign and then back to minus cosine. So you get the same thing but minus, but 2 chain rules, so 2 2's pulls out a 4. Minus 4u, of course, is what that is. But anyway, the point is if you add them, it's harmonic, right? Hence, uxx plus uyy is equal to 0. Hence, u harmonic. And where's the harmonic on? In fact, it's harmonic on the whole complex plane. Yes, sir.
So then the entire function f would be
No guessing. No guessing. No guessing. Let us derive it.
Oh, okay, we're not supposed to know that yet.
I can guess it, but that's because I made up the example. You guys are supposed to derive it for the moment, but
That's fine.
at some point or another, I do want you to see past deriving it to see to guessing it. I mean, I do want you to see the man behind the curtain here, which isn't hard to see. So we have to solve these two equations, right? We have to solve ux is equal to vy, and we also have to solve that uy is equal to minus vx, right? Those are partial differential equations we have to solve in principle in order to find the harmonic conjugate. If you do that, then u and v satisfy the Cauchy-Riemann equations, and as they're continuously differentiable in the plane, certainly they form a holomorphic function, an entire function, u plus iv, if we can solve these. In fact, we can, right? So what's this say? This says 2 e to the 2x cosine 2y is equal to minus partial v partial y. And this tells me that minus 2 e to the 2x sine 2y is equal to partial v partial x, right? And I seem to have put the minus on the wrong one for some reasons I don't entirely understand. I don't know where that minus came from. I'm sorry about that. The minus was supposed to be on both sides of the second one. The minus on the left-hand side comes from differentiating cosine. The minus on the right-hand side comes from the Cauchy-Riemann equations themselves, which we're trying to satisfy. Have you ever solved problems like these before? Yes, you have. This is exactly the calculation you saw in Calculus 3 when you were, say, given, here's a conservative vector field, find the potential energy function for it. It's exactly that calculation. You're trying to find some function that when you differentiate, you get back to the vector field. It's not, I'd say it's like that. It's not quite exactly that in our current notation, but the calculation is very similar. We can solve these by doing integration, holding one variable fixed, right? Yeah.
No, I'm wrong.
Oh, you're wrong?
Yes.
Okay.
Carry on.
So if I integrate 1 holding x fixed, it gives me that v of x comma y is equal to what? If I integrate both sides holding x fixed, what do I get? I get e to the 2x cosine of 2y, right? Plus what? Plus some function possibly of x, right? Because if I'm holding x fixed, my constant's actually is some function of x. And then you can plug this into 2. Plug into 2, what do we get? Partial v partial x is what? It's equal to 2 e to the 2x cosine 2y plus dc1 dx, right? Because the partial derivative with respect to x of c1 is a total derivative. And what's that all have to be equal to? Oh, I'm sorry. And I canceled the minuses on the 2. Equation 2, if that's all right with you guys. So partial v partial x is supposed to be equal to what? It's supposed to equal to 2 e to the 2x sine 2y, right? I think I did something wrong here. Yeah, I did something wrong. Oh man, come on guys. This is what I get for not writing it out. I said integrate with respect to what? With respect to y holding x fixed. So is that the right thing? No. What should this be? If I integrate with respect to y, I don't get, I get minus, well, I get 1/2 sine, right? So I should have sine of 2y there.
And that's why your 2 in front of e to the 2x in a way is 1/2 times that.
Right, if I take the partial derivative of this with respect to y, I get back to here. So you can see it solves equation 1. And of course this was a sine. So differentiate with respect to x, we get this, because the sine stays alone because it's a function of y. 2 pulls down because e to the x differentiate, e to the 2x differentiate pulls out 2. And this is all supposed to equal to e to the 2x sine 2y, yeah. Of course, what happens? These guys cancel and we get dc1 dx is equal to 0. Therefore, c1 is just some constant, right? In fact, the harmonic conjugate's not unique. You always have some freedom in the selection of a harmonic conjugate. You can shift it by a constant, at least that much. Let's see here. So what do we have? We'll choose, let me just choose c1 equals to 0 for the sake of our convenience. And what do we have? We have u plus iv is equal to e to the 2x cosine 2y plus I e to the 2x sine 2y. Can you recognize what this is? This is e to the 2 times x plus iy. This is e to the 2z. So the point is just this. If you have a function which is harmonic, you can solve the Cauchy-Riemann equations to find its harmonic conjugate. And then if you look at u+iv, that gives you an example of a holomorphic function, which has both of these things at once. So what's the significance of harmonic conjugates? Like what, apparently every complex differentiable function we get on a domain, in other words, every holomorphic function we have on a domain, it's got a pair of harmonic functions in it. They solve Laplace's equation, which is kind of cool, right? Because Laplace's equation, for example, if one application of this, if the electric field is minus the gradient of some potential energy function phi, this is the electric potential, then the divergence of the electric field is minus the Laplacian of phi. And so in the absence of charge, that's equal to 0. In other words, these are voltage functions on a domain without charge. So every holomorphic function comes with a pair of the component functions can be understood to be the voltage functions associated with some two-dimensional electrostatic problem. There's also an interpretation in terms of fluid flow, stream functions versus the flow functions. We'll see that. I'll talk about that more in another lecture. But the applications are vast. But let's think about a more basic question, like geometrically, what's going on here? What's the relation of a function and its harmonic conjugate? Okay, that we can understand somewhat easily. So if we look at u of x comma y equals to, say, some constant k1, and if we look at v of x comma y equal to some constant k2, these are what? It's the level curve. Let's call this level curve 1. Let's call this level curve 2. Right? And I'm going to assume what? F equals to u plus iv is holomorphic, okay? Or let's just say, I get sick of writing that, is f an element of the holomorphic functions on some domain D? Which is just a lazy way of me telling you that both of those are solutions to the Cauchy-Riemann equations on some open connected set. What's the relation geometrically between these level curves? Do you guys remember how level curves work? Maybe, maybe not. You have to put them in Mathematica. Is wrong, is the wrong answer. You don't need Mathematica. You just need your mind. So if this is u equals to some constant k1, what's the gradient of u looks like this, right?
So can I just write my mind for question 29?
Oh, well, I think that one, I recommended the use of Desmos, which has less licensing issues than Mathematica. But
I might try that.
it's free. So
Is it sort of more point and click?
well, I'll get it out here in a minute or two. So we'll see. So these amoeba-like looking things. My point here is, if this is v equals to k2, these red arrows are the gradient vectors to v, and over here you have the gradient vectors to u, right? Now you remember that they have to be perpendicular. There's a simple calculation that shows this, right? If I have a parametrization of one of these level curves, right? If this is, say, gamma of t, then what does it mean for gamma of t to be a parametrization on this curve? It means that u of gamma of t is equal to what? U of gamma t is equal to k1 for all time in the parametrization, right? So if I have some parametrization of a level curve, it means if I feed the parametric formulas into the level equation, it solves it. But on the flip side, I can differentiate this. And when I differentiate this, I get the chain rule. The chain rule tells me that if I differentiate this with respect to time, of course, I get the gradient of u at gamma of t dotted with d gamma dt. Of course, that's also equal to 0 because k1's a constant, right? Which goes to show you that, of course, the tangents are perpendicular to the gradient wherever you look at if you look at a point, pick a point, any point on the level curve, look at the tangent to a parametrization of the level curve as contrasted with the gradient at that set point. They will be perpendicular. Chain rule, just that. Now, just reminder, okay? What does it mean then if we compare what would you say? Forget about tangents for a second. How would you compare the geometry of the level curves u, level curves v directly without using tangents? What would you do? Tell you what, let's calculate the gradient of u dotted with the gradient of v and see what we get. This would be what? Ux, uy dotted with the vx, vy, right? Two-dimensional calculus of two variables, right? As the gradient vectors, vector fields technically. Take this dot product, what do you get? I almost agree with you. Ux times vx plus uy times vy. But these satisfy the Cauchy-Riemann equations, right? So what do you want to? We can get rid of something here. Let's see. What do you want me to keep the u's or keep the v's?
U's.
Keep the u's. All right. It's very. So this would vx is equal to what?
Equation 3, where is it?
If you know nothing else for the next test, you should know this. I think it's minus vy, right?
I have flashcards.
Oh, minus uy, right? Minus uy. You have flashcards.
I haven't memorized them yet, but I have them.
And then vy is equal to ux, right? So this is 0. What's that say? They're orthogonal. So if you look at the level curves of the real part of if you look at the level curves of harmonic conjugates, right, u and v, they meet perpendicularly. Assuming what? I mean, there is an exceptional case here. What if the derivative is 0? Then I really can't conclude that. I mean, it's still true that the gradient is perpendicular, but geometrically, if the gradient's 0, I kind of lose track of what the curves look like at that point. Yeah. Mm-hmm.
So if all holomorphic functions have u and v harmonic functions,
Yeah.
and then the level curves of the u and v parts of a function f are perpendicular to each other.
Yeah.
Then
Excuse me.
that means that like the graph of the level curves for the real and imaginary part of a function are constantly going in opposite directions.
That's right. The level curves of the real part and the imaginary part, wherever they meet, are like exactly perpendicular. They meet at right angles. It gives you some sort of orthogonal web of curves.
Okay.
I mean, these give you the orthogonal. In other words, if you've had differential equations or maybe calculus 2 recently, the v's are orthogonal trajectories to the u. Level curves of v are orthogonal trajectories to the level curves of u. Now, what does it mean for mapping to be conformal? Conformal. So here's the deal. If I have two curves, gamma 1, gamma 2, all right? And so here's maybe, the v1, here's the tangent to v2, gamma curve, gamma parameterized curves. These parameterized curves, let's say, end at this point P, right? And so the end tangent to gamma 2 goes in the v2 direction, the end tangent to gamma 1 maybe goes in the v1 direction like that, right? Then a mapping f is said to be conformal if when you look at the composed curves, like the image curves, f composed with gamma 1 and f composed with gamma 2, and you look at the corresponding intersection point over here, f of p, right? Then over there, you have, of course, these new, you have the, let's call it v tilde 2 and v tilde 1. All right, so the velocity vectors of the transformed curves. The mapping is said to be conformal if when you look at such a situation, the angle between the original two curves is the same as the angle in the transformed pair. So if you want, I could say theta tilde. Conformality is just theta equals to theta tilde. It's a pretty simple consequence of the formulas I showed you last time, guys. And I'll let you read my notes on this, but basically this is it. Theorem, if f prime of z is not equal to 0, then f is conformal at z. I'll call it z naught. At z equals to z naught, it helps me talk. What does that mean? The proof of that is fun. It involves the, basically just calculate the dot product between two tangent vectors and the dot product between the two imaged vectors. I use the chain rule over here and things cancel. It's not that complicated. Maybe I'll do it next time. I want to show you some pictures this time, and the time remains, so I'll do the proof of this next time. How about that? But the application is huge. If you think about it, right, if I look at this web of horizontal and vertical lines in the domain, right, and if I have a holomorphic function f, which is, suppose it's, f prime of z is not equal to 0, on this web, then what does it give you over in the this is the xy plane. Over here in the uv plane, what do you get? I mean, I don't know what you get exactly, but if this is the one curve, then the other ones have to somehow meet. I can't do it very well, but these are supposed to be right angles everywhere at intersection. Right. If it's conformal, the angle of intersections are preserved. So it says that it takes an orthogonal web to an orthogonal web wherever the derivative is non-zero, which is very interesting. Let me show you some pictures. So you guys, modulo some little justifying arguments, and I'm sure I forgot to say something today. We're almost done. We have one thing left, major thing left, which is the fractional linear transformations. There's also an example I should show you while we're waiting for my computer to behave and this. Let me show you a quick thing that will help you with one of your homeworks on this current homework, I think. How would you show cosine squared z plus sine squared z is equal to 1 on all of z? Here. Now, of course, you could just work it out algebraically, but here is a lazier way, which is far easier. Let this be f of z, right? Calculate f prime of z. What is f prime of z? Minus 2 what? Minus 2 cosine z, sine z by the chain rule, plus 2 sine z, cosine z, again by the chain rule, which is otherwise known as, to quote my friend Dipul Guhar Sarkar, 0. It is 0, as you can see. Haha! On where? On the complex plane, everywhere. This is connected. Hence, by the theorem last class, what is f of 0? Come on, computer.
1 plus 0.
Which is?
1.
Right. But this is a constant function, as we just proved, because its derivative is everywhere 0 on a connected domain. So sine squared plus cosine squared is 1. This is an example of, this is a nice way. Oh, let's not look at the naughty list. Let's see here. it's a nice, really beautiful way to see that cosine squared plus sine squared is equal to 1 without a lot of tedious detail. This should be an obvious hint to you about the cos squared minus sin squared problem in your homework, right? So here actually is gory details. I look at the z squared function, and the u and the v for the z squared function are either x squared minus y squared or 2xy, right? If you look at x squared minus y squared equal to a constant, you get hyperbolas which either open around the x or y axis. If you look at 2xy equal to a constant, you get hyperbolas which are rotated like 45 degrees. Either, they're the reciprocal functions. And then if you graph those, they look like this. So here I'm looking at the hyperbolas which open one way, and then some of the reciprocal functions. And as you can see, wherever these meet, 90 degrees, right? These are the graph of the harmonic functions inside the z squared function. And there's one point which is kind of screwy, which is the origin, which is where f prime of z squared is equal to 2z, which is equal to? At the origin, it's 0, right? That's where the conformality, well, that's where the perpendicularity of the actual coordinate, the level curves, breaks down, is where the derivative is 0. But now I answer the reverse question. So what if you look at, if you think about that, what if I look at where u is equal to a constant and v is equal to a constant in the uv plane? I get these curves. This is, let's see here, what is this? Oh, actually, I think I missold this. These are actually parabolas, and well, I'll read my notes. Anyway, you can see it's perpendicular. I think this is actually what I was just talking about. There it is. There's the picture of the hyperbolas about the x-axis and y-axis, and the ones rotated by 45 degrees. As you can see, they meet at perpendicular. And so, let's see here. This next picture, I'm looking at the e to the z and what it maps the xy coordinate grid to. So xy coordinate grid, of course, meets at right angles, right? When you look at its image under the exponential, you get this thing. So, I'm bothered by the origin at the moment for some reason. Well, don't let me be bothered. So next time, I'll talk about fractional linear transformations, and I'll probably I probably shouldn't do. Let me just let you read the notes on the conformal proof. It's not that hard. If you have questions about it, you can ask me, and I'm just going to go straight to section 2.7, so we have a whole class on that. It's very computational, and I think you'll like it. So anyway, I will stop there. Thanks, guys.
So at this point, is the test just slated for next Wednesday?
Yep.